All right, so today we're starting back in section 3.4. We were looking at graphs of polynomial functions, and we had done a couple of graphs. We talked about symmetry. We talked about x-intercept behavior, which we had talked about before. And then we talked about this end behavior idea. And we used those three features, plus some additional points here and there as needed, to construct graphs. And we did this graph. We didn't need any additional points. But on this graph, we did need a few additional points to make it a smooth curve. So we're going to jump in on this example. This one is very nicely already factored for us, so we don't have to do the factoring. And so we're going to start with symmetry, like we have done on the earlier ones, just going in the same order. So first of all, symmetry. And if you'll remember, when we look at symmetry, we look at evaluating by plugging in negative x and deciding whether or not we have the same function that we had when we put in positive x. So here's negative x at the beginning. Here's a negative x plus 6 in the middle. And here's a negative x minus 7 at the end. So the problem on this one, because it's in factored form, is it's really hard to know whether or not this has symmetry. Right? It's not in a form that it's easy to determine. Definitely the sign changes on the whole thing because of the negative on the outside, but it's possible that some of those pieces inside changed, but not all of them as well. Does that make sense? I can't look at this and know for sure if all the signs, when I multiply it out, are going to have stayed the same or going to have changed. It's not determinable. So this is, I'm just going to write down right now that it's difficult to determine. In a moment, we'll see that it's really very clean without multiplying it out when we do our x-intercepts. So let's actually jump across to number 2. We'll go back and answer whether it has symmetry or not in a moment. Let's look at number 2, which is our x-intercepts and the multiplicities. So if we were to take this equation and set it equal to 0, it means that we set each piece equal to 0. So x is equal to 0, x plus 6 is equal to 0, and x minus 7 is equal to 0. Notice I've put the powers on there just to remind us we are going to have to remember to write down the multiplicities based on those powers. So this one, of course, is just a multiplicity of 1. This one, if I take my square root, I just have x plus 6 equals 0. I subtract my 6. So x is equal to negative 6. But what's the multiplicity on this one? Yep, it's a 2 because that power of 2. And then on the last one, again, x minus 3 will equal 0. I add my 7. So x is equal to 7. And what's its multiplicity? 3. So I'm going to plot those x-intercepts first, and then we're actually going to be able to answer the question from part A based on just those x-intercepts, and I'll explain why. So if I have a 0 here, I'm supposed to have a negative 6. Let me change colors so that it's differentiable. There we went on there. Here's our point here, and then I'm supposed to have a positive 7, right? Yeah. Okay, so just with those points right there, is it even? It's not, because even means it has to have the same image on the left and the right, right? They have to be mirror images of one another, so that if I folded it over, it would land on itself. Because it's 6 on one side and negative 6 on one side and positive 7 on the other side, those are not mirror images, so it's not even. Odd means that it has to be able to be rotated, which is the same problem. If I were to rotate this 180 degrees, this point that's at 7 would rotate over here to negative 7 where I don't have a point. So this is not even and it's not odd, and I can decide that very quickly from this. Now, if it matched up on the left and the right, I would have to go a little further to decide, does that mean it's even or does that mean it's odd? It would potentially be one or the other at that point. But this one fails both of them immediately. So this one is actually neither. So I'm going to write down that it's neither, and we did that based on, we decided that based on the x-intercepts. All right then, our last thing to do, I also should mention or remind us that we need to decide whether things bounce off the graph or whether they cut through the graph. So if it has a multiplicity of 1, does it bounce off or cut through? Don't remember? Has to do with it's even or an odd. Which one's which? Nobody wants to talk to me today. What is it? It cuts through. You're right. Yeah, so if it's odd, it cuts through, which means that it cuts through at the 0, and it also cuts through at 7. And because we have a multiplicity of 2 at the x equals -6, this one will be bouncing. Okay, so just as a reminder to us, you don't necessarily have to write that down, but I think it's a good trigger to remember when we're looking at the graph and drawing out the rest of it later. All right, so our next thing that we needed to do is we needed to do our end behavior. So our end behavior, step 3, as you'll know, it relies on the degree of the polynomial. Well, because this one's not multiplied out, I don't have the degree written out explicitly. But if you were to imagine multiplying this x times this x squared and this x cubed, that's what it would happen if I multiplied everything out. Eventually somewhere I would have x squared, and I would have x cubed. And what would that be if I combined those exponents appropriately? X to what power? 6. And you'll remember we add exponents, so this x to the 1, x to the 2, and x to the 3. 1 plus 2 plus 3 is 6. So this is even, right? So with even degrees as the degree of the polynomial, they either both point up or they both point down. And it's based upon the sign. Now, the sign in front of this one was positive. The sign here, because I'm squaring things, gives me a positive. And the sign here, I'm cubing, but it's a positive already, positive. So I have a positive. So will my graph both point up, or will it both point down? Up. So I have, my end behavior is that I have both ends pointing up. So just visually, I'm going to sort of draw this over here to remind myself that at the ends, I need to be going upward. So what does that mean? Well, at the end, I need to be going upward on the far left, but I have to be connecting at this point -6. But when I get to -6, it has to bounce off the graph. So this side right now looks something like this. Make sense? Obviously, it's now in an upward, motion. It's going up, but it has to come back down and cut through at the x-intercept right down here at 0. So my graph, we don't know how high it comes up, and it's really irrelevant. Also at x equals 0, I'm supposed to be cutting through. So my graph will actually cut clean through that one again. And then I'm going to come over here to this particular point, right? It's got to come down a ways. We don't know how far, and that's okay. But eventually it has to rotate back around and come back up. And at x equals 7, it's supposed to be cutting through as well. So the graph ends up looking something like this. Again, the scale may not be right. It may not cut through smoothly over there at 7, but that's not really the point. The point is whether or not it has those specific features, cutting through, bouncing off, ends up, ends down. Those are the features that we're looking for when we're doing our graphs, our sketches of our graphs right now. Any questions on this one? It's also worth noting that if you look at this graph and you go back to the symmetry issue, where we only looked at the x-intercepts, it's very obvious by the time we get to the graph that there's no symmetry going on here, right? It's certainly not symmetric on the left and on the right. And if I rotated this around, my ends would be pointing downward, both of them, so it doesn't have the origin symmetry either. So we can also confirm at this point, if we hadn't already confirmed it before, that it is in fact neither in terms of the symmetry. Any questions on this one? Okay, one more question in this section that we're going to take a look at. It's a question about inequalities. We looked at solving inequalities previously from the perspective of testing points and plugging numbers in and seeing what happened. Y'all remember doing that? Right, we created this number line and we did this little test points and we put them in and we said, do we get positives or negatives? Are we looking for positives or negatives? And we made our determination like that. So I mentioned at the time, but I didn't go far enough down sort of the bunny trail to talk about it in depth, that there's a way to do this with graphs too, and we can sort of think about how the graph overlays on that. And specifically, remember having a conversation with Aaron about it as we drew this sort of graph visually a little bit on top of it. And so we're going to look at it from a graphical perspective in this section, now that we've talked more about graphs in general, and take a look at where we can use that information to determine the same sort of features instead of using the test point method. So on this one, we actually graphed this before. We graphed it last time. It was problem number 1. Okay? So I'm borrowing the same information because I'm not doing the same thing again. I don't want to have to go through all the steps, but I want to show you how we can use those graphs and make the same kind of determination. So this image that we have right over here, our graph, is what we're going to use over here. So here's my graph. I need to put my axes back in because that didn't copy paste. It looked like that from the first problem. So if you were doing this polynomial from the graphical perspective instead of from a test point perspective, and you're looking for where it's greater than or equal to 0, or greater than 0 on this one, excuse me, then you're looking for where it is above the x-axis. Does that make sense to everybody? Right? Positive means it's above the x-axis. So the portions of the graph that we're looking for are sort of, I'll highlight kind of the area. It's this area, right? So it's all of these values and these values. So just like when we talked about increasing and decreasing, constant, and then also we talked about domain, we're always giving our answer in terms of x. What x values does this happen for? So on this graph, we see that their x values start here, and then I hit 0 again there. What x values did that represent from this equation? Where does it start? Yeah, so on the far left, it starts at -1. Right? This value right here is -1. And you're exactly right, Cole, it ends up over here at 1. So from -1 to 1, I have graph pieces that are above the x-axis. I have to use parentheses because the question itself asked for strictly greater than. Okay, we've talked about that a number of times now. But I also have all the pieces over here that are above the x-axis. So while I don't get to use x equal 1 because it equals 0 when x is 1, right? It isn't greater than 0. I have a union and I move on and I say also everything bigger than 1. So 1 to infinity. So it might be worth noting, since I've said it but I haven't written it, if things are greater than 0, it means that you're looking for things that are above the x-axis, right? It means y values are positive, so you're above the x-axis. If you're looking for places where it's less than 0, it would have been below the x-axis. And if you were looking for pieces where it was equal to 0, you would be on the x-axis. Any questions about how to use the graph now to think about being above and below, greater than or equal to, less than or equal to kind of stuff? Okay. So this one will be due next class period. We finished it. We're going to actually move on into the next one next.